So today in this lesson, we are going to continue our discussion of atomic theory, and some of this might look familiar to you if you took chemistry. So in the very first lesson on modern physics, we talked about Dalton and his believing that atoms were indivisible spheres, which was later overturned because J.J. Thomson performed his cathode ray experiment and discovered the electron. So after his cathode ray experiment, J.J. Thomson's model for the atom was called the plum pudding model. So he discovered a negative electron, but he knew that overall an atom was neutral. So he reasoned that the electrons were like little raisins embedded in plum pudding, which is this nasty British dessert. Okay, and so the electrons are embedded into a really diffuse positive charge, but the net charge is still zero. Okay, so this was J.J. Thomson's model for the atom, called the plum pudding model, and it looks something like this over here. Okay, the red being the really diffuse positive, and the yellow being the electrons. Rutherford, he performed something called the gold foil experiment. And really what he wanted to do is he wanted to prove J.J. Thomson's experiment. So if we look here, this is a setup of his experiment. He shot alpha particles, okay, which are positively charged particles, at a piece of gold foil, which is made up of gold foil atoms, and wanted to see how they behaved. Okay, so let's go ahead and watch this simulation and listen to what his results, his expected results were versus what he got and what conclusions he made based on that.
In the early 1900s, J.J. Thomson proposed that an atom was a uniform sphere of positively charged matter in which electrons were embedded. This model is sometimes called the plum pudding model. Electrons are embedded in a sphere of positive matter, similar to raisins in plum pudding. In 1910, Ernest Rutherford, Hans Geiger, and Ernest Marsden carried out experiments in which very thin foils of metal were used as targets for alpha particles emitted from a radioactive source. Click on what Rutherford expected to observe, the results Rutherford expected based on Thomson's model of the atom. Based on Thomson's model, Rutherford expected that the positively charged alpha particles should pass through the uniform sphere of positively charged matter with little or no deflection. Click on actual experimental results to see what actually happens. Rutherford observed that the majority of alpha particles penetrated the foil either undeflected or with only a slight deflection. Every now and then, however, an alpha particle was scattered or deflected at a large angle. In some instances, an alpha particle actually bounced back in the direction from which it had come. This was a most surprising finding, for in Thomson's model, the positive charge of the atom was so diffuse, or spread out, that the positive alpha particles were expected to pass through the foil with very little deflection. Upon making this discovery, Rutherford exclaimed, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you." Click on Rutherford's model to see the model of the atom that Rutherford proposed based on his experimental observation. Based on the results of his experiment, Rutherford postulated a nuclear atom. All of the positive charge and most of the mass of the atom is concentrated in a very small volume called the nucleus. Electrons occupy the remaining space of the atom. The radius of an atom is approximately 20,000 times larger than the radius of the nucleus. Most of the positively charged alpha particles pass straight through the diffuse electron clouds of the atoms. Some alpha particles pass close to the small positive nuclei and are deflected at large angles. A few particles score a direct hit on the nuclei and come almost straight back.
Okay, so that describes Rutherford's experiment. So based on his experiment, Rutherford actually discovered the nucleus of the atom. So came up with a new model for the atom, being that all the mass was centered or was concentrated at the center in the nucleus, and then the electrons, which are very small and essentially massless, are in clouds around the nucleus. Okay, so Niels Bohr came up with the next model of the atom, sort of refined Rutherford's experiment by looking at the information from the photoelectron effect and by understanding the spectrum of an atom. So this might look familiar if you've taken chemistry. If not, this will be new. Okay, so his model was called a planetary model, where electrons were restricted to these specific energy levels. So it would make sense that if you were to apply a certain amount of energy, okay, so if we're to look over here at this would be energy in the terms of like gamma radiation, and it were to strike that electron, then a certain amount of energy would be required for that electron to be removed from the atom or ionized, okay, which we saw in the photoelectric effect, using light or radiation to cause those electrons to jump off. Okay, now if the electrons can also be hit by a certain amount of energy, okay, and that can cause the atom to become excited or in an excited state. So the electron doesn't actually fully leave, but it just jumps to a higher energy level. Okay, so as if the electron were to jump to a higher energy level, okay, if it is to fall back down, then some of that energy needs to be released somehow, and it's released in the form of a photon of light. Okay, so energy is put into an electron to make it jump to a high energy level, and then as it falls back down, the electron then releases a photon of light equivalent to the energy required to jump. So what this results in is a spectrum of light, okay? And this is the hydrogen spectra. On top, you see the absorption spectra. All of the color shows the wavelengths of light that are absorbed by hydrogen, okay? On the bottom, you have the emission spectra. So these are the wavelengths of light that are emitted by the hydrogen. Okay, so essentially what these lines represent is they represent electrons that have been excited by some energy and then falling back to their ground state and emitting a photon of light equivalent to some wavelength or frequency based on the amount of energy it needed to jump in those specific energy rings that Bohr predicted. Okay, so this will look really familiar to you if you took chemistry, from me especially. Okay, this model was on the back of your reference table. So this is how we looked at it. This is a hydrogen atom. A hydrogen atom has one electron. So in its ground state, it is located in the lowest energy level, which is N1. Okay, if we apply energy to that electron, then it can have any jump path to any sort of higher shell. So it can go from N1 to N2 or from N1 to N3. If it's at N2, it can jump to N6. So there's all these different jump paths that it can have. The reason why the arrows point down is it's because when the electron falls back down to its original state, that it emits light, okay? And this right here is the spectrum, and you can see that these numbers here correlate to wavelengths. So this is in the visible light spectrum, okay? This is in the UV, and this is in the infrared. So based on the structure of the hydrogen atom and the size of those shells and the energy of those shells, the electrons absorbing and then emitting energy creates this spectrum of light. Okay. Now, in physics, this is how we look at a Bohr's model. So it's a little bit different, but it is essentially the same. Okay. So here you can see that this is N1, just like this is N1 here. This is N2, N3, N4, all the way to N infinity. Okay, that's the shell number. Okay, also called the quantum number. And you can see here that the N1 has a negative 13.6, and that is an electron volt. So that's the energy at N1. Okay, really what this number means is that is the ionization energy for hydrogen. How much energy does it take to make hydrogen an ion, to completely remove that electron? Okay, and it would take the most energy the closer you are to the nucleus. Remember that the nucleus is positively charged, the electron's negatively charged, so there is an electric attraction of force, an electric force holding that electron in that place. Okay, So if you imagine this negative 13.6 being like the bottom of a well, it takes 13.6 electron volts for this electron to escape the well. Okay. In the second shell, okay, which is higher up, you are further up the well, so it would take less energy, 3.4 electron volts, for you to completely escape. Okay, these numbers here come from this equation, okay, where energy is equivalent to negative 13.6 electron volts divided by n squared, so the quantum number squared. In the lab that we are going to be doing in the next class, we are actually going to be using this equation in order to determine or make a Bohr's model like this of the hydrogen atom. Okay. We will also be looking at emission spectra, and we did this in chemistry if you took my chemistry class. Okay, so now maybe it will make some more sense since you've learned some more things about quantum physics. Okay, and we're going to be looking at the wavelengths of light that are being emitted by hydrogen as it's being excited and by other elements. Okay, and we are going to determine the energy, okay, the change in energy that is resulting from the jump of those electrons. Okay, so on Friday, we will be performing a lab in which we make a model like this, as well as relating the atomic emission spectra to the energy of those electrons.